Hey everyone, it's Ariel Herrera here, your fellow data scientist with the AnalyticsAriel channel, where we bridge the gap between real estate and technology. And today we're going to be going over a visual introduction to machine learning. So I stumbled upon this blog a couple days ago, and it's really neat because they've actually put together a seamless page where you're able to interpret machine learning with no code whatsoever, only through visualizations, through D3 visualizations. So I think this is really going to be able to help whether you are experienced with machine learning or you're a beginner to it, just to get an overview of what it is and how these models actually work. So it's going to be using real estate data, and at the very end it shows you how a model makes a certain decision. It's important for us to be empowered and to know what machine learning is and its capabilities and what it does so that we can actually utilize this technology. So before I get into it, please like this video and subscribe to our channel because this is what helps us bring more content to you and also to rank higher in the YouTube algorithm. All right, so let's get started. In machine learning, computers apply statistical learning techniques to automatically identify patterns in data. Patterns in data is the #1 thing about machine learning. For me and you, when we first started walking as kids, right? How did we learn to do that? Well, we had to practice. We learned to fall, we learned to crawl, and we also had people teach us how to walk. For a machine learning model, think of it as a child. You had to actually feed it life examples in order for it to interpret how to go about the actions. As I go forward, it says these techniques can be used to make highly accurate predictions. And what we're going to be using is a data set about homes, where we will create a machine learning model to distinguish homes that are in New York versus homes that are in San Francisco. But first, a little bit of intuition. In machine learning, there's different types of ways that you can train a model. And in this particular case, we're going to be going over a classification task. Classification is just basically being able to put a label on your data set. So say if we are watching a Netflix movie and we wanted to decide based on all these traits about Betty, do we think that she has watched already Grey's Anatomy or not? So that's a yes or no label that would be applied. And then if we were doing unsupervised learning, that would be something that has no labels. So for example, if we wanted to recommend Betty a show, we can try to see people that were like her, what kind of shows that they watch, and put her into that type of group. So that's just the distinction between those two. So in this case, we're going to be labeling whether a home is in San Francisco or in New York. So since San Francisco is very hilly in comparison to New York, we use this first as our distinguisher between these two. So as you could see on the left, San Francisco is in green, and on the right, New York is represented in blue. And we have a distribution of their elevations. So San Francisco, the homes are a lot higher. At the height, we have 744 feet. And then for New York, they relatively stay around here. So the darker it is, the higher counts or more number of homes with this much elevation. So they say here, based on home elevation data to the right, you could argue that a home above 73 meters should be classified as 1 for San Francisco, because we could say if it's above 73 meters, it is likely always San Francisco. Now, adding nuance. So we can't just base our decisions off of one single feature, right? That wouldn't make sense, just only solely through elevation. So here we add a second dimension. For example, New York apartments can be really expensive per square foot. So visualizing elevation and price per square foot in a scatter plot, which is what is on the right, helps to distinguish lower elevation homes. The data suggests that among homes at or below 73 meters, those that cost more than $19,000 about per square meter are in New York City. So we have here on the bottom, on the x-axis, the per square foot value, and then on the y-axis we have elevation. So we basically have taken these two, what they call features, predictors, or variables, just something to describe the data that we're looking at, and we've put this into a 2D plot. So we have two different features here. And we're able to now separate this data based on these features. So we're drawing a boundary now. So you can visualize that when elevation is greater than 73 meters, which is going to be this whole green area, and price per square foot is greater than 19,000, which is this whole blue area on the right, that it really helps us to distinguish only homes that are in San Francisco and only homes that are in New York. Whereas we see still in the white part on the bottom left-hand corner that it's very messy still. We haven't clearly defined how to separate these two, which is why we need additional information. So the next thing we're doing is we're getting more features to actually look at. So the data set we're using to create the model has 7 different dimensions. Creating a model is also known as training a model. On the right, we are visualizing the variables in the scatter plot matrix to show the relationships between each pair of dimensions. So for example, let's say this plot over here. This one, you can see the green and blue are very separate. They're not mixing in much. And that was the features that we previously used, elevation and price per square foot. You could also say the same for price and square foot. It seems like blue, where New York is, it's clearly above, has a higher price per square foot versus San Francisco. And there are clearly patterns in the data, but the boundaries for delineating them are not as obvious. And that's where machine learning comes in. It helps us to be able to understand these relationships between these different features. So say if we didn't have the domain experience of real estate, or maybe we weren't able to interpret how all these features relate to one another, machine learning can help us do that. So finding patterns in data is where machine learning comes in. Machine learning methods use statistical learning to identify boundaries. One example of a machine learning method is a decision tree. This is probably one of the most simplistic guesses for machine learning. Decision trees look at one variable at a time and are reasonably accessible. Okay, so we're going to look a little bit more at this. So finding better boundaries. Let's revisit the 73-meter elevation boundary proposed previously to see how we can improve upon our intuition. Clearly, this requires a different perspective. So, by transforming our visualization into a histogram, we can better see how frequently homes appear at each elevation. While the highest home in New York is 73 meters, the majority of them seem to have far lower elevations. So let's pause here for a second. So if you guys aren't familiar with histograms, no problem. Histograms basically is counting the events that occur within each of the ranges. So say down here is going to be 0 elevation, up here is going to be the highest elevation, which I think was about 700 feet or so. And what we're saying is that New York, where you see it populated in blue, New York tends to skew to the left, where that elevation is smaller. And if you look, it's this high peak right here. This means that most of the homes have this amount of elevation. They don't show us a number here, but say if this was like 50 feet, then we would be saying this is where most of the homes lie. They lie in this region, this area. So your first fork. The decision tree uses if-then statements to define patterns in data. For example, if a home's elevation is above some number, then the home is probably in San Francisco. Let me put another example to this. If-then statements. So say when you learn how to drive and you're making a right turn, how do you decide if you're going to do that? Well, if there is no car coming on your left side, then turn. Or else, if there's a car coming on your left side, don't turn. That's a very simple if-else statement, and that's basically what this decision tree is doing, except the output's not going to be turning right or not. It's going to be San Francisco or New York. So machine learning, these statements are called forks, and they split the data into 2 branches based on some value. The value between the branches is called a split point. Homes to the left of that point get categorized in one way, while those to the right are categorized in another. A split point is the decision tree's version of a boundary. So in this case, we go back a little bit. So what this model did is that it split by 242.8 feet. It said everything above that is going to be San Francisco. Everything below it is going to be labeled New York. Now, it's only correct 63% of the time. right? Because on the right, yes, that rule is always going to be true, or it seems to be for the data set that we have. It's always going to be San Francisco. So you see here 47 and 0 New York, so that's great. But on the left side, we have an issue. So it says here, picking a split point has trade-offs. Our initial split at 73 meters incorrectly classifies some San Francisco homes as New York ones. So we see 92 homes were actually said to be New York, but they really weren't. So that means our split was 63% correct. And this leaves us with false negatives. So you guys might be familiar with the term false positives. For example, if you were to go into a hospital and were told that you had cancer, but you didn't, and you went through all that treatment for nothing, that would be a false positive. So they told you that you were positive, but it was actually false. In this case, it's the reverse. So it was actually, you were told false, however, it was true, in fact. So we were told that these weren't San Francisco, but in case they actually were, and we don't want to miss these. So this is on the other side, the false positives that I just mentioned. I'm going to go through more. Okay, so the best split. At the best split, the results of each branch should be homogeneous, or as pure as possible. So we don't want to see 63%. We want to get to the best split as possible. In this case, it's going to be 82%. So when we shift our split, instead of it having it being, what was it, about 242 feet, now we have moved that to 91 feet, so we shifted it to the left. We still are misclassifying some, but not as badly as we were before. So that's good. And we're going to keep adding splits in order for our data to be able to get to be labeled correctly. So if we go to recursion, to add another split point, the algorithm repeats the process above on a subset of data. The repetition is called recursion, and it is a concept that appears frequently in training models. So we continue to do this not just for the elevation, but across all of the features that we have. We will make different splits, or the model will be doing that. So the best split will vary based which branch of the tree you are looking at. For lower elevation homes, price per square foot is at about 1,000 per square foot is the best variable for the next if-then statement. So the if-then statement will be based upon the split. So we're going to keep going. And here, growing the tree. Additional forks will be adding new information to increase a tree's prediction accuracy. So we're just continuing on this journey of splitting the data in order for the tree to improve its accuracy. At this point, it's at 84%. We keep splitting, and now we're at 96%. And then we continue splitting even more, and now we're at 100%, which seems great. Don't we want to be at 100%? Not always, which I'll explain in a moment. So these ultimate branches of the tree are called leaf nodes at the very end. Our decision tree models will classify the homes in each leaf node according to which class of homes is the majority. And this is a really neat visual here. It basically shows you how each of these data points that you put through, it's going to go through these if-else statements. And at the very end, the model labels it either yes or no for New York. So either New York or it's going to be San Francisco. So it goes through. We're training the data. This is called training data because it's used to train the model. And because we have 100%, we grew the tree to 100% accuracy, this tree maps each training data point perfectly to which city it's in. We want to do well to stuff that it's never seen before. So what we do is we create a separate data set called a test data set, something the model hasn't seen, and we see how well is it performing. And in this case, it's performing 10% worse than it did on the training data, which means it's overfitting. What is overfitting? It is too tight on the rules. We have too many rules, and it's only relevant for that particular data. Let me take a step back. So say if we're going to our example of creating a model for driving a car. Now, what if we have all these features? We have the light, we have the time of day maybe. So we put the time of day because maybe the likelihood of being able to turn right decreases when it's rush hour because there's more cars coming. But what if our model makes a split where it's like between 12:51 p.m. and 12:52 p.m., then don't turn right. Like, that's way too nuanced, and we don't want that. We want it to be able to be generalized, and that's basically what we're trying to prevent is overfitting. In this case, we overfit. And there's many different ways you can resolve overfitting, which is a little bit out of scope here. But just to summarize, machine learning identifies patterns using statistical learning in computers by unearthing boundaries in a data set. Simply, it learns patterns, and it does so in a way that makes it where us as the humans, it's a little bit more difficult for us to say, oh, this is how all 8 features or all 8 data points relate to New York and can label New York and San Francisco. It's hard for us to do that, especially if we're not maybe 20 years in the real estate game. This is why machine learning can be really beneficial. One method for making predictions is called decision trees, which uses if-else statements. And this is wonderful because we can actually trace back to why a model made a certain decision. And then lastly, overfitting happens when some boundaries are based on distinctions that don't make a difference. So you can see if a model overfits by having test data to flow through the model. I know this might have been a little bit more detailed for those of you who may not be in the computer science space. Well, that's why AnalyticsAriel is here, to be able to translate this technical concepts into a way that's easily interpretable. And we do a lot of solutions around this space. So please feel free to reach out to me through my website, AnalyticsAriel.com, where we can set up a meeting to talk how we can make solutions for you. So please subscribe, and thank you so much, guys.